Hello everyone, I am K. Sai Namrata Chaudhary from ITB section with roll number 22BQ1A1283. Today I would like to tell about solving recurrence relations using characteristic rules. There are some steps for solving recurrence relations. First of all, here we only discuss about the linear recurrence relations. First of all, homogeneous recurrence relation. Here if f of n equal to 0 in this equation, then the recurrence relation is said to be the homogeneous recurrence relation. First of all, what is homogeneous recurrence relation we have discussed. There are some steps for solving these homogeneous recurrence relation. First of all, write the characteristic equation from the given recurrence relation. Suppose let's consider the recurrence relation to be like this: an equal to c1 a n minus 1 plus c2 a n minus 2. Here the degree of these recurrence relation is 2. So we get two roots. Let us consider those roots as R1, R2. Write characteristic equation from the given recurrence relation. The characteristic equation is R square minus C1 R minus C2 equal to 0. Then find out the roots for these equation. Based on the nature of roots, we write complementary solution. If the roots we obtain are real and distinct, then the complementary solution for the given recurrence relation is an equal to alpha 1 r power n plus alpha 2 r1 power n plus r2 power n. If the roots we get are real and distinct, then the solution is an equal to alpha 1 r1 power n plus alpha 2 r2 power n. Here alpha 1 alpha 2 are the constants. If we get roots as equal, suppose r1 equal to r2 equal to r, then the solution is, complementary solution is an equal to alpha 1 plus alpha 2 into n into r power n. Suppose if we get complex roots, that is root solution is an equal to r power n into alpha 1 cos n theta plus I into alpha 2 sin n theta. An equal to r power n into alpha cos n theta plus I sin n theta. Then for homogeneous solution, the final solution is an equal to the complementary solution we obtained. Next, going to non-homogeneous recurrence relation. If the equation is of the form an equal to c1 a n minus 1 plus c2 a n minus 2 plus so on plus ck a n minus 1 plus f of n, and f of n should not be equal to 0, then the recurrence relation given is said to be the non-homogeneous recurrence relation. Here we have some steps for start. Here we have some steps for finding non-homogeneous recurrence relation. First of all, let us consider the recurrence relation to be this. First, find homogeneous relation for the given recurrence relation. That means using these steps, find the homogeneous recurrence relation. Then based on the function f of n, if f of n equal to an square plus bn plus c, then we need to replace f of n with an square plus bn plus c in an and find the values of those constants and obtain the particular solution. If f of n equal to any constant term, then replace it with a. If f of n is any exponential term or algorithmic term, then replace it with a into e power n in this recurrence relation an and find out the values of those constants and obtain the particular solution. Then the solution for non-homogeneous recurrence relation is complementary solution plus particular solution. Let us take the problem an equal to 3an minus 1 plus 2n. First, here f of n is not equal to 0. So it is non-homogeneous recurrence relation. Let us apply the steps we discussed about to find the solution for this recurrence relation. First, move this term to this side. Here n minus 1 equal to 0. So n equal to 1. That means the given recurrence relation is of order or degree 1. Then find characteristic equation, which may be written as r minus 3 equal to 0. Then root r equal to 3. Here the root is real and distinct. So solution is an equal to alpha 1 into r1 power n, that is 3 power n. This is the solution. Here f of n equal to 2 power n. So if the given function is any algorithmic term or exponential term, then replace it with a into 2 power n in this an. Then an can be written as minus 3. This we can get a value. Then here take 2 power n as common and it get cancelled, and we obtain the equation as like this. Solving this, we get a value with a equal to minus 1, then particular solution be like this. And as we have discussed before, non-homogeneous recurrence relation consists of general solution as complementary solution and particular solution. So this is the required solution for this recurrence relation. Next, I am going to tell about graph definitions. First of all, what is a graph? Graph is a set of vertices and edges in which vertices are connected with edges. Suppose let's consider a graph like this. Here A, B, C, D. These are all said to be the vertices, and these vertices are connected with each other through edges E1, E2, E3, E4. Here let us consider the edge E1, which is connecting the two vertices A and B. So here graph is a collection of set of vertices and edges in which vertices are connected with edges. Going to different definitions of graphs. First of all, adjacent vertices. If a edge is joining any two vertices, then those vertices are said to be adjacent vertices. So here AB vertices are joined by the edge E1. So these two vertices are said to be adjacent vertices. Like this, these two vertices, these two and these two. Next, adjacent edges. If a edge is joining any two vertices, then that edge is said to be adjacent edge. In other way, we can say that any edge is incident by two vertices, then that particular common edge is said to be the adjacent edge. Here E1 is incident by both A and B vertices, so it is said to be adjacent edge. E2, E3, E4, so like that. Next, directed graph. If the edge between two vertices is directed, then it is said to be the directed graph. That means a graph with directed edges is said to be the directed graph. Here all the edges between the vertices are directed, so it is said to be the directed graph. Undirected graph. A graph whose edges are undirected is said to be the undirected graph. That means here the edges of graph does not have a direction. Next, weighted graph. If a graph whose edges are weighted, it's said to be the weighted graph. That means if some edges are located, if some weights are located on edges of graph, then this is said to be the weighted graph. Here 4 is the weight of edge between A and B. So this is said to be the weighted graph. Next, multi-line graph. If more than one edge is used to join two vertices, then it is said to be multi-line graph. Suppose consider like this. Here AB vertices are joined by E1 and E5. So this is said to be the multi-line graph. Next, mixed graph. A graph in which whose edges are directed and some are undirected, then that graph is said to be mixed graph. Consider the graph like this. Here E1, E2 are edges are directed and E3, E4, E5 are not directed. So a graph with both directed and undirected edges is said to be the mixed graph. Next, symmetric directed graph. A graph in which all the edges are bidirected is said to be a graph in which all the edges are bidirected. Then it is said to be the symmetric bidirected graph. Let us consider the graph like this. Here the edges between A and B are E1 and E4 in which both are bidirected. That means it is having forward edge and backward edge. So this if all the edges in the graph are bidirected like this, then that graph is said to be the mixed graph. Sorry, symmetric bidirected graph. Next, degree of graph. Degree of graph is nothing but the number of edges incident on that particular vertex is said to be the degree of vertex, and the highest degree of vertex is said to be the degree of graph. So for this particular vertex, the degree is said to be 2. As 2 vertices are incident on this. For B, it's 1. For C, it's 1. So highest degree is degree of vertex here. So it is taken as the degree of graph. This is for undirected graph. Subgraph. If a graph is drawn from a part of the graph is said to be the subgraph. Suppose a graph is like this. If we draw a graph like this from this particular graph, this is said to be the subgraph of this graph. Next, complete graph. Complete graph is a graph in which there is a vertex. Now, a graph G is said to be the complete if there is an edge from every vertex to all other vertices. Then it is said to be complete graph. Let us consider graph like here. There is an edge from A to B and A to C. Like that, every vertex has an edge to other vertices. So it is a complete graph. Next, wheel graph. A graph G is said to be wheel graph if adding a vertex to a graph, existing graph, can join or form vertices. A graph G is said to be wheel graph if adding a vertex to existing graph forms a edge to all vertices. Then those graph is said to be the wheel graph. Let us consider a graph to be like this. Now adding vertex C. With here it is connected to both vertices B and A. So this graph is said to be the wheel graph. Complement graph. A graph G is said to be complement graph. A graph G is said to be the complement. For example, complement graph. Complement graph is nothing but drawing edges which are not found in the existing graph. Suppose consider a graph like this, then complement graph might look as like this. So this is the complement graph. Next, planar graph. Planar graph is a graph in which adding a vertex to the existing graph without cutting the other edges is said to be the planar graph. Suppose I want to add edge from A to C, then I can add it like this. That means it does not cut any edge. So it is said to be the planar graph. Thank you.